Let us begin the day with God. Settle down wherever you are. Feel relaxed as we begin the new week. Let us pray to God that we can be more productive this week than the earlier weeks, that we may learn new things and try to apply them to help others. Let's pray together. Our Father, who art in heaven, hallowed be thy name. Thy kingdom come, thy will be done on earth as it is in heaven. Give us this day our daily bread, and forgive us our trespasses, as we forgive those who trespass against us. And lead us not into temptation, but deliver us from all evil. Amen. Sorry. So, good morning once again, everyone. So, as you all can see, is anyone trying to join? That we are nearly at the end of the first chapter called semiconductors. Hmm. And I told you all that if you can understand this chapter, then at least you won't have any trouble understanding the operation of any semiconductor device. Now, how you would like to apply it, that's your choice, right? So today we will be looking a bit deeper into this topic, current voltage relation in a PN diode. Am I audible to everyone?
Yes, sir.
Yes, sir.
Okay, fine. So, what is a diode? Current voltage relationship, I think that's not a new term. So, diode is nothing but this thing. The PN junction that we were studying, the doping things, everything, when we would be using it for our benefit, when we'll just put some metallic leads out here, says the P side is the N side, then this is nothing, it will act as a diode. And the symbol of a diode, you know these things, is like this. This is the P side, it is the N side. Okay. So what does a diode do? We all just went through the graph that in forward bias it will heavily conduct, and in the reverse bias it conducts very small amount of current. Yeah, definitely there's a breakdown after a point, but we won't entertain that thing. So diode is a semiconductor device that aids
So,
it's yes.
so I think Priyam is trying to join. So, can I check now?
Is it? Oh, acha. Yeah, right. Actually, I can keep an eye on the focus. Okay. Yeah. So it is a device. Good morning, PM. That will aid, or that you can say it supports good conduction. When I mean conduction, I am obviously talking about conduction of current in one direction only. That is, we are talking about the forward bias direction. I think everyone is okay till here. Oh, Vibhushit is also here. Good to see him. Is everyone okay with this?
Yes, sir.
Yes, sir.
These are very trivial things. We have already, uh, while discussing depletion region, its width, height of the barrier potential, we have come across all these things, right? So now I want to use this thing. I was studying what is happening inside. Now I want to use this thing in an external circuit as a circuit component. So very simple circuit I will draw, though in reality it is not that simple. We require some modifications. So if Vd is the voltage which is applied, fine. For the timing, I would be writing P and N so that you all don't get confused. Later on, I'll omit it. So Vd is the voltage applied. Then there will be a current flow across the diode in this direction. Can you tell me what kind of biasing this is? Is it forward or reverse bias?
Forward by, sir.
Yeah. Don't ask. Don't ask as a question. Yeah, you're right. It's forward bias. P is given positive. N is given negative. Okay. So this is the forward bias case. No. So current will flow. And what is the reverse bias circuit? Same thing. Pn. P side is getting negative. N side is getting positive. Voltage Vd. But still there would be a flow of current. Can someone tell me why did I write S for this current? What is the name of this current in reverse bias?
Saturation coins.
Yeah, what kind of saturation? There's a name. Not only saturation. It is the reverse saturation current, isn't it? Remember everyone? Am I audible?
Yes, sir.
So there's a reverse saturation current. Can anyone tell me what is the source of this current? Why is it flowing? What causes this flow?
Holes, sir.
No, holes electrons are there. Why not electrons?
Because it has like saturated, no, sir. Like the
Yeah,
minority carriers are almost filled up, no, so that's
right.
why.
Minority carriers, right. It is due to the flow of the minority carriers. And it is called saturated because it doesn't depend on the voltage that you are applying. It solely is a function of the number of minority carriers on either side and adjusts the temperature, which gives them the sufficient thermal energy. Clear?
Yes, sir.
Now, a very important thing, the diode current, especially in the forward direction, which is ID, to be very precise. Let me see if someone is trying to join. Yeah, Tithi. Oh, am I muted? That because now it's fine. Actually, if you want to be very precise, you have to write it like this: that the current through the diode in the forward bias direction. Good morning, Tithi. Is actually the majority current. I mean current due to flow of majority carriers minus current due to flow of minority carrier. That is minus Is. It is the exact equation. Okay, this is the exact current equation because we have when we studied how depletion region was formed, there only we saw that If majority carriers are going this way, then minority carriers are going the opposite way. I hope you all remember.
Yes, sir.
Now, this thing also we studied that the minority carriers are very, very less in number, and the reverse saturation current is nearly of the order of microampere if you're using a silicon PN junction, and of the order of as small as nanoampere for its German sorry germanium analog. And also we saw that the order of the majority carriers, rather, it is of the order of milliampere. So there is no harm if we say that, yeah, this ID current flowing through the diode in the forward bias is nearly equal to the current due to the majority carriers only. Am I clear?
Yes, sir.
Okay. We'll be discussing little uh, what if we consider this approximation and what if we don't. Anyways, now there is a formula or a relationship which whose derivation is not required. If you're very much curious, we can discuss it after the syllabus is over. That is the current voltage relationship in a diode, semiconductor diode. It's better to use the word semiconductor diode, okay? Because diode is something I told you which will allow flow in one direction only. It can be anything. Even our human body has diode is also called valve sometimes. So better to mention semiconductor diode. However, diode is I mean, widely used term that people understand that you are talking about semiconductor diodes alone. Still, so the current relationship is like this: I D equals to IS. ID is the current flowing in the forward bias is equals to e to the power k Vd by t minus 1. I'll explain the terms. Don't worry. Where ID is the, we can call the forward current. That is current during the forward bias. Forward diode current. IS is the, I am not writing in detail, reverse saturation current. I think you all understand what it means. Vd is the voltage across the diode. Obviously, we are talking about the forward bias thing. T is the temperature in Kelvin. I need not to give any description to this. Still, I am talking about if you have T degree Celsius, then this is this much in the Kelvin scale. Now, K is a term which is a bit confusing. Confusing in the sense that different books have different expression to this. Okay, not different expression, I would say. Uh, this equation, in fact, has different expressions. So it, you can say it's a constant, and K is equals to 11600 by eta. Now, what is eta? Eta is something called the ideality factor. There's a huge topic on this ideality factor. For the time being, it would be sufficient for you to remember that this ideality factor tells us that how much our given diode behaves close to an ideal diode. Okay, hence the name. and it has a ideality factor, has a range between 1 to 2. Okay, and ideality factor is 1 for germanium, 2 for silicon at lower currents. When the current ID is low, okay, you can use this thing. You have to use this thing in fact. And when your ID, the diode current is high, you have to use 1 for both silicon and germanium for high ID. Okay, basically it is a constant. Got it? So if nothing has is stated, then you have to understand that you would be using ideality factor as 1 if it is silicon, if it is germanium, and 2 if it is silicon. And if that, yeah, when the diode current is low. For high diode current, you have to use it 1 irrespective of the type of semiconductor used. Clear, everyone?
Yes, sir.
Actually, this thing comes in the competitive exams sometimes. Okay, when you have to use this ideality factor value, most of the times they give the value, but still we should not expect that we'll be getting it. Now let's relate with something that we know. Hmm. So what we have this expression. We have k, which is equals to 11600 by eta. Okay, then what would be k by t? 11600 by eta into t. Okay, in some books they have used t subscript k, which means temperature in Kelvin. Let's not complicate that. Okay, now this thing is nothing but we can call it Vt. Vt is the thermal voltage, sometime it is called. Where Vt is nothing but P by k times eta. Why I am writing this thing? You might be getting confused, but in exam sometimes see in this expression there is no trace of eta. But if you use this substitution, you can directly get eta. You need not to work so much. Okay, has everyone copied till this? I have to flip the page to make things more clear.
Yes, sir.
Okay. The expression that I'm going to write now is more common in many books. So I feel you should all know this expression as well. So what we just got, we got that Vt is how much? E by eta k, right? That is what we got with Vt. Check with the focus just a minute. Surrounding light is too much. Is my isn't my screen a bit blurred? Kind of. Can you see it clearly? Is my screen visible properly?
Not that clear as before, sir.
I think,
But
yeah,
it's
it's.
readable.
Wait. I think it's regarding the it's to do with the focus thing. Yeah, now it's clear, right?
Yes, sir.
Unfortunately, I can't move too much in this range. Okay, anyways. So therefore, we can rewrite the equation like this: e to the power Vd by eta Vt minus 1. Just check with the equation that we derived it earlier. Is it okay with that? Is it fine with the substitution?
Yes, sir.
Good. So depending on the question that you get, you can use this formula. Okay. And can anyone tell me what is the value of Vt at room temperature? Any idea? Any idea? Any guess? What is the room temperature in Kelvin?
300.
So room temperature is 300 Kelvin. Hmm. So if I try to find the value of K, it would be, sorry, what was the value of K?
11600
By
by eta.
11600 by eta. Yeah, fine. Uh, what was Vt? By eta K, right? So eta, let it be. So just tell me the value that you are getting here. Unit would be definitely volt. Tell me what is the value.
0.026.
0.0.
26. I rounded it, so
Yes,
I rounded it off.
you rounded it off. Okay, no problem. How much will this be in millivolt? How much in millivolt?
So 26 point something.
So yeah, it's an approximate value. Can anyone tell me what is the name of this thing? Go to Einstein's relationship. This thing has a name. It has a name. Anyone? Yes, anyone? What is the name of this thing? No one remembers. What is this thing called?
So I remember the equation, sir.
You remember the equation? What was it? No, no, I'm not asking Einstein's equation. Relation, I'm asking this thing was there in Einstein's relation. Forgot this thing, volt equivalent of temperature. KT by E. Forgot this thing. That was Einstein's relationship. dP by mu P or dN by mu N, whatever. That is equals to this thing. Now remember this.
Yes, sir.
Yeah, you got confused because I used a different notation here. VT. So just be very careful if you are using this expression, hmm, which is I feel very easy to remember as well. VT would be this only when you are in room temperature. Okay. Else you have to use VT is equals to T by eta K. That is T by this much volts. Okay. Many students get confusing, especially in the competitive exams. Okay. Sometimes we blindly put the value of VT without looking into the temperature. So this is the main formula. VT is equals to T by 11600. Are you getting it? What I'm telling?
Yes, sir.
And that is the reason why nowhere in the books you will find this thing by this thing. Because the same reason many students will get confused. They already know volt equivalent of temperature is 26 millivolt, but that is in room temperature only. Okay, so this is about the diode equation. And what we do, we would be doing this approximation very soon. That uh, now I need to increase the altitude. Yeah. Now this approximation is always taken that uh, let us multiply e to the power Vd by eta Vt minus Is. I just multiplied. So we just put it like this. Since we know that the forward current is much greater compared to the reverse current, reverse saturation current. Okay, got it? What I have written?
Yes, sir.
Fine.
So we can
Now let
approx
us,
this, sir.
yes, yeah, there won't be any harm. We would be doing this approximation very often, and sometimes we do it, we take it for granted. And if you want to plot this graph in the forward direction, you will get something like this. Plot I and V this way, Vd. Better to write ID and Vd. You'll be getting like this. So now, when talking about approximations, is it necessary to take it, or let me reiterate the question the other way around? Uh, what if we don't use the approximation? Why we use approximation? Because see, approximation is used when the reality is very complicated, hmm, or it carries some unnecessary terms, and for simplicity, we do approximation, isn't it? Is there any other reason to
Yes, sir.
do to take approximation? I don't think so. approximation, estimation, these are taken like that. Estimation we do in in a in advance. So with that thing, let us see what is basically the thing without approximation and what with the approximation. That is, what is the ideal situation and what is the practical situation. Okay, so what is the ideal diet and what is the practical diet? I hope you are getting what I am telling. See, both the cases, the diet is nothing like. Let me use a fresh page. So I'm talking about, let's take a diode in forward bias. I don't think anyone has any doubt regarding forward and reverse bias. If you have any doubt, please get it clarified right now. Any doubt, anyone, with forward and reverse bias?
No, sir.
Okay, great. Let me draw the thing very simplistic way. So I have positive on the P side, negative on the inside. The voltage across the diode is Vd, and I have a current flowing this way. Okay, no approximations made. That is what happens. Reverse bias, the opposite kind of uh, biasing or application of voltage and current flows.
Excuse me, sir. Is this for
Yeah, yeah.
ideal, sir?
In general, okay. I'm talking about forward and reverse bias with the circuit symbol. Fine.
Okay, sir.
Only a diode, not ideal or practical. Yeah. Now will come the case of ideal and practical diode. Since our subject is practical oriented, let us begin with the practical thing. So for a practical diode, what we would write? We would write this equation that ID is I major minus I S. Why? Because practically we know there is maybe very negligible amount of current flowing due to magnetic ideas, but it is not zero, isn't it? Isn't that the case? There is flow
Yes, sir.
is due to magnetic area, but that is not zero. We know we are dealing with $1 billion, but we have $1,000. But we can't say $1,000 is not equal to $0. At the end, it won't count. It won't hamper much, but it does have some effect. Maybe very negligible. And the irony is that this thing in the lab cannot be measured properly. I mean, there would be taking ID as equals to IS only, and this I'm talking in the forward bias thing, and the resistance offered by the diode, the forward bias case is very small, maybe of the order of ohms. This can be measured by using a multimeter. If we have a very good multimeter, we have in our lab, in fact. Okay, so what does this thing mean? That in the forward bias, the diode offers very small resistance, but not zero. Clear, everyone?
Yes, sir.
Great. What happens in the reverse bias? It ha- it has very small amount of current flowing, hmm, which is very small, This very small, these things doesn't count unless we give the, estimate value of the order of microampere or nanoampere, depending on the diode you're using, but not zero. And the resistance that it offers in the reverse bias is very high, as high as say mega ohm. Okay. In fact, Bikramjit sir taught you how to detect or identify the leads of a diode. Those who have done it, you will remember that sir just measured the resistances. Hmm. Reverse bias gave resistance in mega ohm and forward bias gave in ohms. Okay, clear everyone?
Yes, sir.
Yeah. Now come to the ideal case. So ideally, or if something we had called an ideal diode, ID would have been solely due to flow of majority carriers. See, ID is not a problem. Whether you take it approximately or exactly, it will give you current only in the milliampere range. Okay, nothing problematic with that. What is important is that the ideal diode will have no resistance in the forward direction. Got it? What will happen if there is no resistance in the forward direction? I mean, what happens if there is no resistance?
All the current flows through it.
Exactly, very good. All the current will flow. And for the reverse bias case, it is taken as the reverse saturation, no current flows there, it is zero. Hence, the resistance is infinite. So we have infinite resistance in the reverse bias direction. Now this is the ideal case. Am I clear? This is what we mean by an ideal diode.
Yes, sir.
Let me extrapolate this thing. So when I have an ideal diode, obviously with two region, forward bias and reverse bias. So in the okay, another thing here, by Ohm's law we can say that Vd is zero, isn't it? V equals to IR. If R is zero, Vd will also be zero. I hope you agree with me.
Yes, sir.
Though this thing is not a very, I mean, we are getting overconfident because we can't apply Ohm's law everywhere in the IV curve. We'll see that soon. Still, that's what we, our common sense tells us. Oh, by the way, you if you can remember, you studied also in your school days that diode is a nonlinear uh, device which doesn't obey Ohm's law. Okay, if I plot for normal for an ohmic component like resistance, the voltage current graph is like this, isn't it? V goes to IR, V is proportional to I, or the other way around. I is proportional to V, in fact. It depends which one you are taking as the independent. Both are interdependent. Anyways, but for C, for a diode, not every region is linear, okay? From here to here, you can take it as a linear device, but here this region is non-linear. Non-linear means where I and V are not proportional to each other. Okay,
Yes, sir.
so only in the linear region we can apply Ohm's law. And that's a different issue. So what happens for an ideal diode if I redraw the IV characteristics? So in forward bias, what is the voltage across the diode? 0. But there is current. And actually the current also should be infinity, isn't it? I equals to V by R. R is 0. So the forward bias current is like this. Okay, this graph is a bit difficult to understand. Why? Because the current is along the y-axis only. Vd is 0 and I have huge amount of current. Okay. Whereas for a practical diode, which I'll draw by dotted lines, the characteristic curve is the forward direction is like this, isn't it? Are you getting it? What I'm telling?
Yes, sir.
And for the reverse bias case, I'll just highlight the third quadrant. For ideal diode, the current is always 0. Why? Because it's offering infinite resistance, the reverse bias direction. So this is the IS. Whereas for a practical diode, I do have small amount of current, which is constant. Yeah, I'm not going as far as the breakdown region. So in a nutshell, I think I can say that the ideal diode works like a switch. Why? When I'm putting the switch on, what I get? This is the switch. Yes. I don't get any resistance offered, isn't it? Switch on, the device is on. More importantly, when I turn the switch off, what happens? It breaks the bridge between the in the device, isn't it? R is infinite. Okay, isn't it? Isn't this a switch?
Yes, sir.
Yes or no?
Yes, sir.
Yeah. So some the ideal diode is analogous to a switch. And if I want to draw the total characteristics in one graph, which I told you all to do in the exam, that will only give us the idea about the behavior. So the dark one is for the ideal case, the dotted one is for the practical case. So I hope everyone is clear what is an ideal diode and what is a practical diode. The funny thing is that practically many times we would be seeing the ideal behavior. I mean, we'll be take the ideal behavior of the diode. See, at the end it depends on us. When we are applying something, hmm, uh, we want to use it for our benefit, definitely keeping in mind uh, the basic laws that they are not violated. Hmm. So I think you all are clear.
Yes, sir.
We have another class from 12 today only, so we'll end it here. Let me just recapitulate what we learned today. It is important. So we began with the symbol of a p and diode. This thing we already studied. earlier. We went on to give a very basic definition what a diode or what a diode does in fact. Then we saw the case when the diode is in forward bias and reverse bias. We got this equation. We took this equation for granted. We didn't deduce it. That's not in the syllabus. I would say beyond our scope right now. Then we did some. Oh yeah, before that we came across a new term called the ideality factor, which would be 1 for germanium and 2 for silicon at low diode current, and 1 for both the types for high diode current. Did a substitution where we related thermal voltage with eta like this. Sorry, yeah. We saw that not necessarily all the time this has to be 26 millivolt, and then we ended up with our discussion of a practical and a ideal diode. So in the next class, I want to finish this chapter. I would discuss a little bit about uh, a step junction and a linear gated junction, just a definition, and something called static and dynamic resistance. Fine. If you have any doubt, please ask. What has been taught so far? Anyone having any doubt?
No, sir.
No, sir.
Okay, then let's meet in the next class from 12:10. I
Okay,
hope
sir.
you all
Thank you,
are.
sir.
Thank you, sir.
I hope you all are attending your GE classes. Please don't skip it. GE is also equally important. Okay.
Yes, sir.
Okay.
Thank
Thank
you,
you.
sir.
Then take care.